Assalamualaikum and hi, my name is Muhammad Alif Nazmi bin A. Asmadi and my metric number is AE190018. So I will explain about the manual calculation for the group assignment. So as you can see, this is a RLC, a parallel RLC circuit. We have VS and then we have resistor 50 ohm. For the inductor, we have 0.1 Henry and capacitor 10 microfarad. So based on this graph, we know that for t between 0 and t from 0 to 1, we have 10 volt and we have a 0 volt for 1 until 2. So these are the formula, and we need to find the A naught, En and Bn. So for to find A naught, these are the formula, and then we just input the t, the V supply and so on, and then we have 1 over 2 integrate 0 to 1 10 dt plus integrate 1 to 2 0 dt, and then we have 10 minus 10 over 2 t from 0 until 1, and then we'll get the answer is 5. So for inert we'll have 5. Next one is an. These are the equation, and then we just input the t, the v, 2 over 2 integrate 0 to 1 and 10 cos n omega naught t dt. And then we'll get omega naught is equal to pi, and then an equal to 10 integrate 0 to 1 cos n omega t dt. Then we convert it into sine, so we'll have 10 times with 1 over n pi sine n omega n pi t from 0 to 1, and we just minus these two in terms of this equation, and then we'll get n we'll get 10 over n pi sine with n pi t minus with sine n pi 0 1 0 because these two. So n pi we'll get for the 0 1 2 3 and so on. So the value of an is equal to 0. So next one is bn. These are the formula, and we just input the t, the v, the omega naught. So we'll have 2 over 2 integrate 0 to 1 10 sine and omega t dt. Then we simplify it into negative 1 over a cos at. So as you can see, negative 10 over n pi cos n pi t. So in terms of 0 to 1, so we know that negative 10 n pi times with cos n pi 1 minus cos n pi 0. So since it is the cos, and then we'll have this graph for cos. So n equal to 0 1 2 3 and so on. So after that, negative 10 over n pi times with 1 minus 1 to the power of n minus 1, and we'll have 10 over n pi times with 1 minus 1 to the power of n. So if this n is even number, which is 2 4 6 8 and so on, the bn value is 10 over n pi times with 1 minus 1 equal to 0 if it is the n is even number. So if the n is odd number 1 3 5 7, so we'll get the value for bn 10 over n pi times with 1 minus 1, so we'll get 20 over n pi. So back to the vs formula. After we get the an, bn and a naught, we just input it into this formula, and we'll have 5 plus 20 over pi and equal to 1, which is for odd number first, times with sine n pi t over n. And then we'll have this after we use this formula, we'll get n equal to 2k minus 1. So we have to find the we use the an and bn in order to find the amplitude spectrum. So square root an squared plus bn squared, and then we'll have this range which is the value is 20 over n pi for the n is equal to odd number, and if the n is even number, the value for n is 0. So these are the amplitude spectrum based on this. Then we need to find the phase. These are the formula, and then we'll have this range -90 degree value for odd number and 0 for even number, and then we'll get this phase spectrum. As you can see, for odd number we will have to the negative 90 degree, but for the even number it is 0. Then for S domain circuit, for we just use the previous formula, which is t plus 5 plus 20 over pi, and this for the odd number, k equal to 1 over n sines n pi t, and then we just input the value of n. So we'll get for DC component, the V supply or V node is equal to 5 volt for each load, but for AC component, Vs equal to V node equal to 20 over n pi degree of -90 degree volt. This is only valid for odd number, because as you can see, -90 degree for odd number, but for n equal to even number, the value is 0. So it is only valid for odd number only. So by using those result, we'll get a node plus total n equal to 1, an cos times with n omega naught t plus with the angle. So we'll get Vs equal to 5 plus 6.366 cos times with pi t minus 90 degree, and plus 2.122 cos times with 3 pi t minus 90 degree plus 1.273 cos 5 pi t minus 90 degree plus, and so on. So these are the we know that it is a parallel RC circuit. So Vs is equal to Vr equal to Vl equal to Vc. So next one, we need to find the current of each branch. Current for each branch. This for IR, IL, and IC. So this by applying Ohm's law, V equal to Iz. And then we simplify it because we need to find I. So I equal to V over Z. So for IR, the V is 5 plus 20 over n pi with degree of -90 degree, and we'll divide by Z, which is resistance 50 ohm, 50 equal to, and then we'll get equal 0.1 plus 0.4 over n pi with the degree of -90 degree, and then 0.1 plus 0.4 over pi, and then we times with 1 over n sines n pi t, which is n, and value is 2k minus 1, and then we input. So we'll get the IR respond with t is equal to 0.1 plus 0.127 cos times with pi t minus 90 degree plus 0.042 times with 3 pi t minus 90 degree plus 0.025 cos 5 pi t minus 90 degree ampere, and so on for respond with time. So the last one is IL. I equal to V over Z. So the V is 5 plus 20 over n pi with degree of -90 degree, and I'll divide by the Z, which is imaginary 0.1 n pi. So since n equal to 0 for DC component, and J 0.1 is equal 0.1 with a degree of 90 degree, so IL is equal to 0 plus 200 -90 degree over n squared pi squared. So we just input the 2k minus 1 for the n, and then we'll get the final answer for the current for inductor, which is 20.264 cos pi t minus with 180 degree plus 2.251 cos 3 pi t minus 180 degree, and plus 0.811 cos 5 pi t minus 180 degree ampere, and so on, respond with time. So for IC, for the current for capacitor, the V is 5 plus 20 over n pi, negative 90 degree. For Z is equal to 100k minus j n pi. So after that, after input the response value and then we simplify it, we'll get 1 over 5k. So simplify it, we'll get 2 exponent negative 4 ampere. So the value for current, capacitor current is 2 exponent negative 4 ampere, respond with time. So the last one is we need to find the power of each load, which is PR, PL, and PC. So these are the formula to find P. And then for PR, we already get the VI, the VN, and IN. Then 5 times with 0.1 plus half, 20 over n pi times with 0.4 over n pi. Then cos negative 90 plus with negative 90 degree. Negative 90 degree. So we'll get 0.5 plus 4 over pi. That's why total n equal to 1 over n. So we know that n is equal to 2k minus 1. We just apply it in this equation, and then we'll have the power for the resistor is equal to 0.5 plus 1.273 plus 0.424 plus 0.255 watt, and so on. Small time. So next one is the power for the inductor. The V is 5. For the IDC is 0 plus 1 over 2 n equal to 1 times with 20 over n pi, and then times with in cos with negative 90 degree plus 180 degree. We'll have the power for the inductor is equal to 0. It is same with the PC. This is 0. 5 times 0 plus 1 over 2 n equal to 1 total times with 20 over n pi times with 2 exponent negative 4 cos negative 90 degree minus 0 cos 90. So the value of power for the capacitor is also 0. So I think that's all from me for the manual calculation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hilmi Haziq bin Afami, metric number AE190048. So today I would like to explain our simulation for the RLC circuit. So using the Proteus software to design the circuit. So first, our VIN, we decide to set the amplitude 10 and the frequency is 0.5 Hz. Next, there is our RLC. The resistor is 50 ohm. The inductance is 100 millihenry and the capacitor is 10 microfarad. So next, we need to measure the voltage of each node, first node, second node, and third node. And next, we need to measure the current at each branch. This is for the first branch, second branch, third branch. And last one is to measure the power. So the result we got is here. Next, I will pass to my friend.
Assalamualaikum, I am Wan Raziman bin Abdul Razak, metric number AE20030. So I will explain about the comparison between manual calculation and simulation result for our group assignment. So as we can see, this is the table for the comparison between calculation and simulation. And the first things, we can see here, this is the circuit simulation that we simulate in the Proteus, and this is the result. We can see here, this is the voltage at each node, first node, second node, and third node. Current for each branch, first branch, second branch, third branch, and power for each load. Here, first load, second load, and third load. So for the comparison, for the voltage, our group use the parallel RLC circuit, which means the voltage at each node will be equal. So that the V supply will be equal to voltage at resistor, voltage at capacitor, and voltage at inductor. So for the calculation, we got the voltage, DC voltage with 5 volt, and for AC voltage, we got the first 3 terms here. And the simulation, we got 3.09 volt. So the difference about 2 to 3 volt for between the calculation and simulation. For the current at the resistor, we get for the calculation 0.1 DC current and the first three term for AC current. And for the simulation, we got 0.062. That's close to 0.1 ampere. So that is about 0.5 ampere to 0.7 ampere difference between calculation result and simulation result. For the current at the inductor, there is no DC current for the calculation, and it's only we can get the AC current for the first three terms here. And for the simulation, we cannot measure the current here because there is an error when we run the circuit. So we just measure the current here and use the Kirchhoff current law to calculate the current at the inductor. And this is the calculation, and we got the result 25.9977 ampere. And it's almost 5 to 6 ampere difference between calculation result for the first term, 20.264 ampere. Next, for the current at the capacitor, we got 0.2 milliampere for the manual calculation, and simulation we got 0.3 milliampere. So the difference is only 0.1 milliampere. Next, for the power for each load, for the first power is for the power at the resistor, we got 0.5 for DC power, and the first three term for the AC power here. And for the simulation, we got 1.1 watt. So the difference is about 0.5 to 1 watt between calculation and simulation. For the power at the inductor, for the calculation, we got 0 watt, but for the simulation, we got 11.6 watt. So that's such a big difference here. As we can see, 0 to 11.6 watt. And lastly, for the power at the capacitor, for the calculation, we got 0 watt, and it's similar to the simulation. We also get 0 watt. So that's all the comparison between calculation and simulation result for voltage, current, and power in this our assignment. So that's all from me. Thank you.